Oh, hello everyone. My name's Roger. I'm a software architect in Oracle's Data and Storage Technology Group. This is how to contact me. My DMs are open on Twitter. You can email me at Oracle. I've been at Oracle for 18 years working on every aspect of the data layer: hybrid columnar compression, in-memory columnar, the column cache on Exadata, table scans, external tables. So I've worked on quite a number of areas, but all to do with how data interacts with the disk. As you can see, it's a bit about myself. I work from home in rural Pennsylvania. Both my neighbors are Amish, so we have horses and buggies going up and down the street outside our house. And as I was telling Aidan a minute earlier, my attempts to remain sane in this career involve taking exotic vacations where I can get completely off the beaten track, and do something that's kind of shakes all the cobwebs out every year. So why this talk? Well, for those of you who know him, I blame Martin Woodlake. My friend Martin gave a talk at an OUG on why white tables are a very bad idea. And he had a point. I mean, I've heard DBAs tell each other that you should never have more than 255 columns in a table. The question is, once you start getting into wider tables, there is a certain amount of housekeeping for the DBA to monitor and to think about. So rather than saying don't use them, I want to tell you how to get the best from them. And I'm sure Martin in a follow-up talk somewhere will disagree. But so let's start with, I spent the last 2 years working on 23C wide tables. And Mike Gleason and myself increased the number of columns in a table from 1,000 to 4,096, a limit which includes hidden columns and virtual columns. We had 3 customers who wanted to move to Oracle but could not until we lifted the 1,000 column limit. So this wasn't something we did just, to sort of tick the box against our competitors. We had real customers who couldn't make progress without this. Previously, the workarounds for people who needed more than 1,000 columns were things like table splitting, where you have split, columns 1 to 1,000 into one table, 1,000 to 2,000 in the next table, or using JSON to add, an unknown number of columns at the end of a table. And with the recent improvements to the JSON data type, particularly within memory and offload to Exadata, JSON performance has become much faster. And the other big change, of course, we had with using JSON to work around the column limit was it's now stored in a compiled data format on disk called OSIN, Oracle Stored Object Notation. So where do all these 1,000 columns go? Some people are a bit surprised when they run into the limit, and there are various reasons. Things like SAP drops columns on compressed tables, for example, and they're converted to unused columns. So they still count towards the column count, even though they've been dropped. Fusion apps recently added hundreds of functional indexes. They use virtual columns, which contribute to the column limit. The blockchain project reserves 20 virtual columns per table for future use. So there are all kinds of things that eat away towards the 1,000 column limit. So we introduced a parameter, requires 23C compatibility. You can play with it in 23C free. Max columns equals extended. You have to bounce the database for it to take effect because it changes memory sizing of some fairly fundamental structures. It does not propagate automatically from CDB to PDBs. So you can set it manually inside each PDB, or you can use the container equals all syntax to force it to propagate to the PDBs. Though I imagine most people only want to set it in a PDB and not the CDB. One of the first questions that customers ask, if I play with this and don't like it, how do I revert it? Well, you can use the same syntax to go back to standard. And if the PDBs don't have any objects with more than 1,000 columns, it will succeed. However, if you have created tables with more than 1,000 columns and haven't dropped them or removed the extra columns, those PDBs will fail their attempt to go to standard, and you'll get Aura 62003, which will tell you how many pluggable databases had issues. You'll have to go to the alert log for the details. The alert log will tell you which PDBs ran into issues. And then the way to work out what objects are stopping you from reverting the parameter is to use the view all tab cols, looking for columns greater than 1,000. And I did want to make this note to use all tab cols and not all tab columns. All tab cols is the one that includes hidden columns and other things that might not show up. So it's the one you have to use when you want a real view of what's going on in the table. We found that with very wide tables, we were getting about twice the performance of JSON, for where you had put the same number of columns into JSON documents. People wonder about performance of very wide tables. For freshly inserted data that's nice and contiguous on disk, there's a linear increase in column access with the number of columns. Because you'd expect that. You're just working through reading row pieces, and the more row pieces you read, the more time it takes in a linear manner. So there's not a lot of degradation, assuming you keep the data unfragmented. This is the slide you don't get from product managers. Any new feature often has some limitations in the first release. The current ones that I know about, the column cache on Exadata might not get built if there are too many columns. It depends on the actual data, and we have a 36 megabyte heap for building the column cache, and if we run out of space in that, building the column cache will fail for that 1 megabyte of disk region. It's possible to run into KGL heap limits. If, for example, one of our QA engineers created two 4,000 column tables and added join conditions on all 4,000 columns. And that broke the 64 KB KGL heap for that operation. My first reaction to that was, if you have 4,000 join conditions, you probably have bigger problems with your schema than worrying about KGL. Offload, we're going to talk about this later in the talk. As tables get wider on Exadata, you need to monitor the stat chained rows skipped by cell. We'll talk about why that is later. And another side of this project is an increase in PGA usage. 23 does use a little more PGA than 21 did. A number of things are statically sized that we had to change from 1,000 to 4,096 because if they're not malloc, we can't malloc them to the size of the parameter setting. And we couldn't change them to malloc for performance reasons. And then if you set this parameter on, again, it will increase the PGA usage a little because the cursor cache takes up more space. So not everyone is interested in block dumps, but I wanted just to have one section talking about block dumps so that if you want to go and see for yourself what's going on disk, about how fragmented the rows are, what the data looks like, why you might be having performance problems, it's good to know how to take a look. To get a block dump, you need the file number and the row 8, the block number. So here, the row I'm interested in is in block 6, but I've dumped from 5 to 7. So the question is, why would I dump the block each side? Well, it depends on whether you're using conventional inserts or direct path inserts. The block whose headpiece is in block 6 might have started in block 5, or it might continue over into block 7. So dumping one block at each side means you're more likely to see the same row without having to go back and dump another block to see where the rest of the row was. Another way to find out what you need to block dump is, there's a little query here which I stole from someone's article. I have this in a Perl script where I just pass in the row ID and it spits out what I need. But the underlying query, if you want to work out how Oracle builds its row IDs in base 64 encoding, it can be fun to work your way through that particular query. And if you wonder why there's so many A's in Oracle row IDs, it's because A is equivalent of 0 in base 64. So just before you start looking at data, there's some security concerns. By default, we prevent block dumps if data is encrypted. All data on the cloud is forced to be encrypted. There is an underscore parameter which can be set at system level to allow the dump of encrypted blocks, but you should obviously only go looking at encrypted data if you have permission. And that parameter cannot be set on Oracle Cloud. There is no way technical support can get a block dump on Oracle Cloud, which can make sometimes working on bugs very interesting for us, because there's no way we can see the data that went wrong. And often it's the contents of the block that tell you what the problem was. But there is literally no way for us to get the block dump. The cloud is really locked down to the point where it can make life interesting for support engineers. Again, I won't spend too long on this because we want to talk about more practical things for a DBA. A block dump has 4 parts, and I'm not going to talk about the first 2 because they're not really relevant to wide rows. We have a cache header. The only interesting thing for this talk is the type, block type, which should be 6 for transactional data. You can skip over the transaction header because that would be an entire talk in its own right. And then you get to a data header, which tells you a bit about what state the block's in. It's got some flags that you know whether row movement's enabled, for example. Where the first free row index in the block is, where the beginning of free space is, where free space ends, and how much available free space there is, and free space after commits. So an Oracle block, the row index starts from the top and data starts from the bottom until they meet in the middle and the block is full. So here's a row. It has some flags, and it has the width of the row that includes the byte lengths. The row flags tell you which row pieces, and I'll explain those in a minute. And it tells you the column count in the row. So trailing nulls won't appear in that column count. So Oracle's row format has 3 parts. a head piece that anchors the row ID, a first piece containing the start of the columns, and a last piece containing the final columns. The reason it's important to understand is how many buffer cache gets to retrieve a row. The more row pieces that a row is broken into by fragmentation, the more buffer cache gets it's going to take to retrieve it. And that does show up on performance. So this is why this talk is going to be talking about fragmentation. We had a customer in the UK who shall remain nameless, who had so many years of updates to this table. The rows were on average broken down into 9 row pieces with only 4 or 5 columns per row piece. And that did explain their performance issues. The other thing to think about, which we'll talk a bit more about in a minute, is the importance of column ordering. If all of the columns you want are in the first row piece, then you don't have to worry about how many other row pieces there are in the row. And it has a direct impact on the Exadata offload model, which we'll again talk about later. So a regular row has an H, an F, and an L flag, head, first, last, and the columns. Nice and simple. If you've got more than 255 columns, or we ran out of space to put the row in a block and had to put the remaining columns somewhere else, you get just a head and a first piece, and then a next RID that points you to the continuation row piece. You can get migrated rows. This is where you, and I'll show you an example in a minute using an update statement, where you go to update a row and there's no way it can fit in the block, and we move the entire row from the first to the last into a different block. And that, if you do a block dump, will have a next RID pointing to where the data starts, and the data will have a head RID pointing back to where the row ID is. So the reason we create migrated rows on an update is if we move the head piece, we have to go and update all the indexes because the row ID would change. And also if row movement enabled is not set, we're not allowed to change the row ID anyway. But it does have some side effects on performance in scans, which we'll talk about. If you've got very wide columns, you've got some varchar 4000s in there, we can end up creating a next row piece where you'll see an N, meaning the last column is continued in the next row piece, and a P saying this column continues from the previous row piece. So we try to split row pieces on column boundaries, but if you've got very wide columns, we won't waste more than 150 bytes. So if moving the entire column to another block would waste more than 150 bytes, we create an N row piece. So this next section is, if you only take one thing home from this talk, I really hope it's going to be the slide after this. Percent free is the amount of space inserts leave for future use. It defaults to 10%. If you update a column to be wider than the remaining free space, we must migrate some or all of the columns to another block. And that's where you start to see row fragmentation performance issues. It's okay for percent free to be 0 if you've got write-only tables. Percent used is how much empty space after deletes there is in a block, at which point we add it back to the free list for an insert to use. And you can see those values in user tables. So the wider a row is, the more critical this next slide is. What is the size of my row when the application first writes it to disk? In an order processing app, you might have a number of null columns at the beginning that are filled in later by business processes. We've also seen some terrible Java apps insert rows entirely null, commit them, and then go back and populate every column, which is literally the worst possible thing you could do with Oracle. What is the size of the row when it's fully populated? At some point in the row's life cycle, all those columns that were used by processing stages will have been filled in, and the row will reach a maximum size in its life cycle. And what is the size of the rows when the business process is complete? Do we null out transient columns that were only of transient use to pack the rows better? I know it's kind of expensive to set a column to null if you're no longer using it, but it does have an effect on the cache lines. If I have column 1 I'm interested in, and column 3 I'm interested in, and column 2 is transient data that's no longer used, I may have to jump to another cache line in the CPU to pull in that next column. By nulling out columns that were only transiently used and are not needed any longer, the rows pack together better in the block and on the memory bus and in cache lines. So this is the thing to take home. Percent free is the difference between the initial size of the insert and the maximum size in a row's life cycle. You're going to hit fragmentation problems, and with the performance impact they bring, if you don't think about percent free as part of your design of a schema, particularly for any tables that have heavy use of updates during their processing life cycle. If you can size percent free correctly right from the beginning, you can pretty much avoid row fragmentation altogether. And the system will hum along much, much more smoothly. So the next thing to think about for a DBA on wide tables is the difference in conventional inserts and direct path inserts, because they have a critical effect when you have more than 255 columns. So I created a table with 260 columns where the first 20 columns have data, the last column has data, and everything in between is null, to give myself lots of space to play with. And what's going to happen if I do a conventional insert is first we write the last piece with 255 columns, and then we will write the head piece with the remaining columns. And it will have the next grid pointing back. Why this layout? This layout is because if we wrote the head piece first, we wouldn't know what to write for the next grid because we wouldn't have the address of the block. After we've written the last piece and we realize we need another block, we go to the free list and it will find the next available item on the free list, which might be a considerable way away on disk. And then we remember the address of the tail piece, and when we're writing the remainder of the row, we can write the next grid in, pointing backwards. Now, here's the performance problem. If I only want to access with this table the first 5 columns in the query, I'll only access the first row piece. I won't have many buffer cache gets. It'll hum along smoothly. But if I want column 7, I'm going to have to read the next row piece, which is 1 additional buffer cache get. So it has, once you go over 255 columns, conventional inserts leave you with a suboptimal layout on disk, where the majority of your columns may be in trailing row pieces that require more buffer cache gets. So that's something to think about. By contrast, direct path loads first write the head piece with 255 columns, and we already know the next grid at that point, so we can write the last piece with just the remaining columns. Why this different layout? This is because direct path insert controls its space before the insert starts. A direct path insert grabs contiguous space above the high water mark and starts laying the rows out as neatly as possible. So now if you do a table scan or a fetch by row ID, and the columns you want are in the first 255, you're not going to need another buffer cache get to get the rest of the row. So just switching from conventional inserts to direct path inserts can halve your buffer cache gets with wide tables. And just to think about costs, if I have a row and I want to get to column 8, I'm going to start at the beginning of the row and walk one value at a time until I get to column 8. And that takes about 8 instructions per value on current Intel CPUs. A buffer cache get for a block that's already in the buffer cache is about 4,000 instructions. And to fetch a block that's not in the buffer cache, it's 190 microseconds on an X8 or X9 that is not under load. Most systems are going to take a lot longer than 190 microseconds. So extra buffer cache gets by not laying out data optimally can have a huge impact on performance. Just clustering the most heavily used rows at the beginning, heavily used columns at the beginning of the row, over time adds up to a lot of CPU time walking the row to get to the columns of interest. And making sure that all of the columns are like, the most heavily used columns are in the first row piece. Again, you can see it has a huge jump in how much time it saves. So again, a thing to take home is column order matters. Understand your patterns of access to columns, which ones the access to them is clustered together, which ones are most heavily used. And we'll talk about, if you have a suboptimal layout, how to fix it in a minute. I talked about migrated rows, and they have an impact on performance. We use a headpiece scan when you ask for the row SCN in a query, or we're running an IMC population, running a hybrid IMC scan where the table is only partially in memory, or it's a PDML combined with select for update. Parallel query that needs the row ID can use first piece scans because it can get the row ID from the HRID back pointer in the first piece. If you want to know whether a scan is using a headpiece scan, you can use kernel data storage full table scan tracing on low. Don't use low est, you won't see anything. And you'll see the TZRH flag at the beginning of the scan. That means it's a headpiece scan. So we create, just to understand in a bit more detail how when migrated rows are created, we create a migrated row if there's not enough space in the block and the block is not compressed and the new row piece is smaller than the block size. However, there is an exception for Exadata table spaces with row movement enabled, and it's not a cloud service, not an IoT, not clustered. Supplemental logging is off, and you're not updating a long column. We will actually try to avoid creating a migrated row, and instead we'll pay the cost of index maintenance to avoid the performance issues of headpiece scans. Again, I don't want to beat a dead horse, but column order matters. The wider the table, the more it matters. So it's not unusual to add a new column to a table, and the new one you're adding is something that's going to be used very heavily. We can reorder a table online to bring the most heavily used columns to the beginning of the table using DBMS redefinition. So that runs online and then has an extremely short blocking DDL where it swizzles the object ID between the old and the new versions of the table. But you can only reorder your columns if all of your insert statements have used explicit column naming. This is something to check with developers. You lose a lot of flexibility if you are lazy creating insert statements. If I just say insert into foo and list all the columns, I now can't reorder foo without having to go back and change every insert statement. If I actually say insert into foo, column 1, column 2, column 3 values, now I can reorder those columns completely and it won't matter because we'll just match up the column name to the column it should go to. So please, if you're looking at wide tables, monitor your insert statements if you have control over them, and I know some applications do not. And make sure that, all new code being written, insert statements should use explicit column names. And, JSON, with the new JSON data type, if you really want to avoid getting into multiple row pieces, you can use JSON for the 254th column and just keep adding columns to that. It's a perfectly legitimate way of widening a table without having to think a lot more about fragmentation, though you still have to keep %free set accurately, which means you still have to understand your row's life cycle. Talking to DBAs, developers, I really don't find people have thought about a row's life cycle very much. And %free, it seems a lot of Oracle customers just leave it set to the default. Again, I've said this before, but you can save yourself a lot of grief by understanding the life cycle of your data. Direct path load, some people are leery of it because of the one-touch rule, that after a direct path load, you can't do anything with that table until you commit the direct path load. I believe that the one-touch PDML rule has been lifted in 23. I wasn't able to check the final status of it in 23.3 before this talk. By using, we now use subsegment merges where each direct path load creates a subsegment, and then at the end of the load, it just merges the subsegment into the main segment so that you can have multiple direct path loads running against the table. That's a feature which customers have been asking for many, many years. Okay. So updates and fragmentation on wide tables. So here's a block I created. It currently has 10% free space. So I have 920 free bytes in an 8K block. I update one of my null values to 881 characters. And now I have 43 free bytes left in my block. Now I update another null to 880. Well, there is no space for it. So here we have a migrated row. We have in this block a headpiece with a next grid, where we had to move our updated data out into another block, but the tail piece is still exactly where it was in that block. So when I go over to look at that other block, I will see the 255 columns that got moved from away from the whole head piece when we migrated the row. And it will have both the head grid pointing back to where the H row piece is and an N grid pointing to where the L row piece is. And you can see they're still pointing to the same two rows they were before we ran our update statement. So now we'll do a buffer cache get. If it's a headpiece scan, we'll do a buffer cache get to the first piece, and then we'll do a buffer cache get to get back to the last piece. So these are a bad idea, which is why %free matters. If you're on Exadata and using a headpiece scan and the migrated first piece is not in the same 1 megabyte chunk, this row can no longer be processed on the cell. It has to be sent back to RDBMS to be processed, losing the benefits of offload. I know there are a lot of people still using 11.2. We recently had a customer who just migrated from Oracle 6 to Oracle 19 in one go, which was quite a leap. If you are on a release older than 12.2, there are some issues with wide tables. Update of trailing nulls created a row piece in a different block. So if you had an application where above column 255, there was a whole load of data that was unknown when it was first inserted, then you go back and populate it, you create a new row piece for every column, which is a bit of a disaster. Before 12.2, the way we search for blocks on the free space for conventional inserts didn't try looking within the local 1 megabyte region first. Before, it used to just find the next available thing on the free list. Now it will try to keep the row pieces close together. And before 12.2, alter table shrink did exactly the wrong thing for Exadata because it didn't try to keep row pieces contiguous. So if you want to use wide tables, please, please, please upgrade to at least 12.2. 11.2 and 12.1 have a lot more issues with using tables above 255 columns. And I think some of the consultants who go around saying you should never have more than 255 columns, probably some of that impression formed by using releases prior to 12.2, before we did a lot of work on laying the groundwork for wide tables. Not going to talk about deletes in detail. When a delete causes a block to have less space used, and it is placed on the free list. When the block is completely empty, it's not released but kept on the free list. A DML, like a delete, can't lower a table's high watermark. Only DDLs can change the high watermark. Well, actually, direct path loads can increase it, but you can't decrease it. Table scans always scan up to the high watermark. We don't know if those trailing blocks are all empty. If you have some kind of life cycle where you insert thousands of rows and delete thousands of rows, I don't know, like tickets for events where you delete the old events and you're adding new events, you can end up with a lot of empty blocks to scan in a table. And we're going to look at how to detect that kind of fragmentation in a minute. So maintaining wide table performance means keeping an eye on fragmentation and compaction. First thing we can do is we can look at some stats. Table fetch continued row tells you, after the first row piece, how many additional row pieces we had to process. Buffer cache gets tells you how often we had to move to a different block to get row pieces. But those have to be put in context. Look at the scan rows gotten, scan blocks gotten, and table fetch continued row and buffer cache gets really table fetch continued row should be compared to scan rows gotten to see if it's a significant fraction, or if you've got more than 255 columns and you're going to have 2 row pieces, you don't want to start seeing that get into 4 continued rows per row gotten. So you've really got to monitor the ratio between them. And the same with buffer cache gets and scan blocks gotten. Comparing buffer cache gets to scan blocks tells you how often we needed a row piece that was not in the block we were looking at. The next thing we can do is we can run analyze table and get the chain count, which again gives us, basically it's telling you the same kind of thing that stats are telling you. Stats tell you what you needed for your actual access pattern. This will tell you how the row fragmentation for the rows on disk. Row piece fragmentation into different nearby blocks. If you're using direct read, we scoop up a megabyte of blocks at a time into a slot array in UGA. And in PGA. And if you need to get a row piece from another block and it was within that 1 megabyte, access to it is still very, very fast, because all we do is walk the slot array to see if we already have that block before we go looking in the buffer cache. So different ways of dealing with fragmentation. There are blocking ways and non-blocking ways. Blocking ways, I think DDLs like alter table move can completely reformat the disk into a nice pristine layout for the rows. ASCAN data pump export and import if you don't have the extra disk space. Non-blocking ways of dealing with fragmentation are DBMS redefinition, alter table move online, alter table shrink space compact, followed by a very quick but blocking alter table shrink space. Some DBAs tell me they can't fix their tables because they don't have any spare disk space. Ways that don't require extra disk space are data pump export and import, shrink space compact, doesn't need any extra disk space, analyze table, and then grab the heavily chained rows, copy them to a temp table, delete them in the original table, and copy them back using a direct path load. Don't copy them back using conventional insert, because all it will do is start looking for blocks on the free list, which will be scattered all over the place, which won't have solved your problem at all. Though I imagine that last one, copying the rows out, deleting them, and copying them back, is one that many DBAs would be very hesitant to try. Requiring 2x disk space to fix fragmentation we have DBMS redefinition and alter table move, because they create a second copy of the table temporarily until you're finished with the operation. Requires more than 2x disk space, alter table move online. It needs more than 2x because it needs an additional 17 bytes for every row to track the where the row ID was and where it is now. So that fetch by row ID keeps working smoothly through an online move. So there are ways to get around fragmentation that don't require extra disk space. So I know some customers, again, have told me they can never fix their fragmentation because they can't allow the time taken for a blocking DDL, like alter table move, and they don't have the extra disk space for move online. I don't know what to tell you other than go back and fix %free so that all the new data isn't getting fragmented the same way. Alter table shrink is a useful tool since 12.2. We can find out how full our blocks are, how many empty blocks we have with DBMS space usage. So all these slides will be going out in PDF format. So you can, you should be able to cut and paste from PDF. What this is only going to work with auto space, segment space management table spaces. I hope you're all on ASSM these days. You can check it by looking in user table spaces. It should say auto. So here I have my fairly full table. Nearly all the blocks are full. Now I delete every other row from the table. And the majority of my blocks are only partially full. So now I enable row movement and shrink space compact, which doesn't move the high watermark and it doesn't invalidate cursors. So you're not going to pay the cost of hard passes after that DDL. And now everything's moved down to the end, and shrink space, the brief blocking DDL moves the high watermark down, and now we have nicely laid out blocks that are full. So it's worth monitoring what happens when you run shrink space compact and shrink space. And the way shrink works since 12.2 is it moves all of the row IDs, the head pieces and the HF rows, from high watermark down to low watermark, and bringing all of their chained row pieces with them to store contiguously. Once it's done as much as it can to get rows contiguous below low watermark, it moves the non-head pieces, any remaining last pieces or other things that were left trailing above low watermark, it moves those down to low watermark. And then it does, you can do the DDL to remove the space between low watermark and high watermark. Okay, last section. Row chaining on Exadata with wide tables. Exadata works 1 megabyte of disk space at a time. If a required row piece is not in that 1 megabyte, we return the block unprocessed to RDBMS. This can, conventional inserts can make this more likely to happen. Whereas with direct path inserts, we always lay things out neatly in 1 megabyte chunks. If you have a row major table, we won't offload a query that references more than 255 columns. So you can have row major data with 4,000 columns, but you can only have a query that accesses 255 of them. Again, once you start getting over 1,000 columns, there are a lot of advantages to using hybrid columnar compression if you can. We're no longer walking the row looking for columns. You can just jump directly to the column of interest with hybrid columnar compression. And hybrid columnar compression has no limits on how many columns can be referenced in a query for it to offload successfully. So we process a row if all of the row pieces for the wanted columns are in that 1 megabyte chunk. Columns we're not interested in, if they're not in that chunk, it doesn't matter. 11203, we did make some change to try and align chain rows better. N row pieces are supported in 12.2 onwards. So it's another reason to upgrade to at least 12.2 if you're still on 11. And it's 3 statistics to monitor with Exadata. Chained rows skipped by a cell. That means we didn't have all of the row pieces we needed in that 1 megabyte. It was the table was, that section was too fragmented, and we sent it back to our DBMS to be processed. Chained rows processed meant we had everything we needed. And chained rows rejected meant that when we assembled the row pieces from wherever they were scattered, they would no longer fit in one output block. Which now in 19C, an 8K block allows up to 32K output blocks. So that happens very, very rarely. We also got around that by, if a query is using row sets, and it's not a headpiece scan, we will pivot an output block from row major to column major before sending it back, because the processing of it when it gets back to the RDBMS is 10x faster. This is why some people get very confused when they only have row major data and start seeing columnar statistics on the RDBMS side. It's because blocks were pivoted from row major to column major after processing in the storage cell. So summary, white tables are very, very useful as long as you're thinking about the issues to do with managing them. Reiterating what I've already said, the row's life cycle, you need to understand your row's life cycle. Try, if you are able to reorder columns by access frequency. Try to use direct path loads, monitor row fragmentation, monitor Exadata offload, and when needed, schedule a compaction using one of the 5 ways I outlined. And that is, with 5 minutes to spare, the end of my presentation. I know we covered a lot of ground. The slides will be sent out. It's available on video if you need to go back and check anything. So are there any questions?